In this video, we're going to explore the concept of stoichiometry. Stoichiometry involves looking at the amounts that are involved in chemical reactions. When we discussed balancing earlier, we talked about the law of conservation of matter tells us that the total mass of reactants that we have must be equal to the total mass of products. And the number of atoms that we have on the reactant side must be equal to the number of atoms on the product side. And that's why we have to balance chemical reaction. The law of conservation of mass can also be used to look at the relationships between the amounts of things in a chemical reaction. And that's really what stoichiometry is all about. When we look at our balanced chemical reaction, the coefficients in front of every product or reactant provide for us a ratio of all of the things that are involved in the reaction. This ratio can then be used as a conversion factor that allows us to convert back and forth between any two things that are involved in the reaction. For example, here we have the combustion of ethane, in which 2 molecules of ethane will react with 7 molecules of oxygen to produce 4 molecules of carbon dioxide and 6 molecules of water. And so if we want to know how many moles of water are produced if we have 3 moles of oxygen present, then we can look at our relationship between water and oxygen in our balanced chemical reaction. And so we can see here that it's a simple matter of setting up a conversion factor that allows us to convert back and forth between the moles of O2 and the moles of H2O in our reaction. And we look back to our balanced chemical equation, and we see that for every 6 moles of water that are produced, we began with 7 moles of O2. And so that relationship becomes our conversion factor. And so if we start with 3 moles of O2, we have to then set up our conversion factor like so. And we see that doing so, our moles of O2 cancel out. We perform the calculation, and we're left with 2.6 moles of H2O produced from 3 moles of oxygen. It's also important for us to note that these conversion factors from the stoichiometric ratio are exact numbers. It is exactly 6 moles of water that are produced per exactly 7 moles of oxygen. Therefore, the significant figures only come into account from the information that we start with. We started with 2 significant figures in our initial measurement. We multiplied by something that's an exact conversion factor, therefore infinite significant figures, and so our answer must be reported to 2 significant digits. The take-home message from that is that these molar ratios do not factor in when you're looking at your significant figures in a final answer. We see here some other conversion factors that come from our stoichiometric ratios. We start with our unbalanced reaction of molecular iodine and molecular fluorine reacting to form iodine trifluoride. We balance our equation, and that gives us a number of stoichiometric ratios. We see that for every 1 I2 we have in the beginning of our reaction, we need 3 F2s in order to react with that. We also see that for every 1 I2 we have, we form 2 IF3s. And for every 3 F2s we have in the beginning, we form 2 IF3s. Remember that conversion factors can be set up however you need in order for your calculation to work out. For instance, we can talk about 1 mole of I2 for every 3 moles of F2, or we could write that as 3 moles of F2 for every 1 mole of I2. It will just depend on what you're looking for in your calculation, how you set that up. So let's look at some examples of how we'll use this. In this example, we want to know how many moles of I2 we need in order to form 4 moles of IF3. We look at our balanced chemical equation, and we see that for every 1 mole of I2 that I start with, I form 2 moles of IF3. And so my conversion factor between the two is 1 mole of I2 to every 2 moles of IF3. Or, depending how I'm going to need it, I can write 2 moles of IF3 for every 1 mole of I2. In this case, our beginning information is our 4 moles of IF3, and I'm looking for I2, so I can see that I'm going to need this form of my conversion factor in order for this calculation to work out. For every 1 mole of I2 I start with, I form 2 moles of IF3. And we can see that our moles of IF3 are going to cancel out. I will be left with moles of I2. And so we perform our calculation, and we find that we need 2 moles of I2 in order to form 4 moles of IF3. Here, we want to know how many moles of F2 are needed in order to form 12 moles of IF3. So we begin with our 12 moles of IF3, and we can see that we're looking now at our relationship between IF3 and F2. And so, in order for IF3 to cancel out, that still needs to go down bottom. So we have 2 moles of IF3 for every 3 moles of F2 in our reaction. We calculate that out, and we see that we will need 18 moles of F2 in order to form 12 moles of IF3. In our final example, we want to compare our 2 reactants. We want to know how many moles of I2 are needed in order to react with 1.5 moles of F2 present in the beginning. And so we see that we need half a mole of I2 in order to react with 1.5 moles of IF3. This question here is very typical of many stoichiometric problems. In this problem, we want to know how much IF3 is going to be produced if we start with 3.24 grams of I2. So let's look at what our strategy is. In order to solve stoichiometric problems, we must go through moles using our molar mass and then use our mole ratios as conversion factors. So again, it's impossible to do that without first having a balanced chemical equation. We need that balanced equation in order to obtain our mole ratios. The pathway we see here will be a very typical path you take when solving these sorts of problems. You'll start out with grams of some sort of given quantity in the chemical reaction. You'll use your molar mass in order to convert that quantity over to moles of whatever you were given. And then we'll use our molar ratio from the balanced equation in order to then convert to moles of whatever it is that we're looking for. And finally, we'll use the molar mass of that thing that we're looking for in order to convert back to grams. When in doubt, mole it out. If you have a situation where you're working on a stoichiometric problem and you don't know where to start by simply converting to moles if you're not in moles already. That will be the first step for the vast majority of these problems. From there, see if you have any relationships you can use in order to find what you're looking for. But this will be the first step in most of your reactions, and so it's always a good place to start. Here's another flowchart for us to look at our relationship. In this flowchart, we're given the grams of some reactant, and then we want to know how many grams of product are going to be produced from that. It is not possible for us to go directly from grams to grams. We simply cannot do that. In order to get to grams of our product, we have to first convert over to moles of the reactant using our molar mass. We can then use our molar ratio from our balanced equation to convert over to moles of the product. Then we can use the molar mass of that product to finally calculate the number of grams. Note that moles are central to our calculations here, and this will be a very common pathway for these sorts of problems. The bottom line is that you first have to convert to moles. Then we can compare the two different things in the reaction using our molar ratio. When in doubt, mole it out. Also note that we're talking in terms of reactant and product in this example, but using stoichiometric ratios and the process that we outline in this video, you can compare any two things in a reaction. You could compare two different reactants, you could compare the amount of product to the amount of reactant, or you could compare two different products. It does not matter. You can compare any two things in a chemical reaction using stoichiometric ratios. And so again, what we'll quite often have to do is our first step will be converting from our mass of whatever we're given over to moles of that thing. We will then use our molar ratio in step 2 to convert over to moles of whatever it is that we're looking for. We can then use the molar mass of that to then find the mass of that thing. So let's take a look at a specific example. We're once again going to look at our reaction between iodine and fluoride in order to form iodine trifluoride. And so, if we begin with 3.24 grams of I2, we want to know how much IF3 is going to be produced. And so our first step is to convert over to moles using our molar mass. Our starting information here is our 3.24 grams of I2, and we want to convert that to moles of I2 using our molar mass. The molar mass of iodine we find from the periodic table. And so we can calculate our moles of iodine. As a side note, you'll notice that I reported my answer here with more significant figures than I had in my initial measurement. When doing multi-step calculations, you never want to round for significant figures until the very end of the calculation. And so in these intermediate steps, go ahead and pull your answers out to more places than you really should, and then save any of that rounding until the very end. So we then move on to step 2, where we're now going to take our moles of iodine and use our molar ratio to convert over to moles of IF3. So we see that for every 1 mole of I2 that I started with, I produce 2 moles of IF3. And so I'm going to produce 0.02554 moles of IF3. And in our final step, we want to take our moles of IF3 and then convert that to grams. We use the periodic table to find our molar mass of IF3. Set up our conversion factor and find that we're going to produce that many grams of IF3. Now is when we want to convert for our significant figures. We began with 3.24 grams of I2 for 3 significant digits, and so our final answer, reported to 3 significant digits, is 4.70 grams of IF3. Now it is also possible to simply set that whole thing up in one long dimensional analysis setup. If we begin with our 3.24 grams of I2, our first step was to convert over to moles of I2 using our molar mass. And then our second step was to convert to the moles of IF3 using our molar ratio. And lastly, to grams of IF3 using its molar mass. And we'll take note, grams of I2 cancel out, moles of I2 cancel out, moles of IF3 cancel out, and our final answer will have the units of grams of IF3, which we're looking for. We perform this calculation, round for our significant figures, and get 4.70 grams of IF3. You'll notice that I was also very careful through this whole setup to write out my entire units of everything. I wrote grams of I2, moles of I2, moles of IF3, grams of IF3, and so on. If you take those extra few seconds and write out your units completely like this, it is much easier to keep track of things through a long problem such as this one. Let's look at another example. Here we have the combustion of methane. And so we want to know if 8.32 grams of methane react, how much O2 is used, and we also want to find out how much CO2 and how much H2O will form. And so again, we walk through the process. Like we said before, our first step is to use our molar mass in order to convert from grams over to moles of our given information. From there, we're going to take our moles of whatever we were given and use our molar ratio to convert over to moles of whatever it is that we're looking for, in this case O2. And we can see that we have a 2-to-1 ratio of O2 to CH4 from our balanced chemical equation. And finally, we're going to use our molar mass of the thing that we're looking for to convert over to grams of that. We also want to know in this example how much CH2 and how much H2O are formed. And so we go through the exact same process. And so here we have the setup in order to find CO2. We first use our molar mass of methane in order to convert to moles of methane, and then our molar ratio, which is 1-to-1 in this example, to convert to moles of CO2, and then finally our molar mass of CO2 to get our final answer of grams. Note here that yes, our ratio is 1-to-1, and so mathematically you don't really need this step in there. However, it's still important to show it and important to get into the habit of writing that in there, because that's our vital step of converting from moles of one thing in the reaction to moles of another thing in the reaction. Here, I want you to pause the video and run through the calculation to try to see how much H2O will be formed. So pause the video now, perform the calculation, and then restart the video to check your setup and to check your answer. And so we find that we'll form 18.7 grams of H2O if we begin with 8.32 grams of methane. If you did not get that answer, look at my setup, compare it to yours, and see where you might have went wrong. Let's look at another example. Here, we're looking at the reaction of molecular hydrogen and molecular nitrogen in order to form ammonia. And we want to know how much H2 had to have reacted if 345 grams of ammonia was produced. And so as we discussed, our first step is going to be to use our molar mass of ammonia in order to convert that over to moles. Our next step will be to then use our molar ratio in order to convert to moles of H2. And then our final step will be to use our molar mass of H2 in order to convert to grams of H2. And so we set up our conversion. We see once again, grams of NH3 cancels out, moles of NH3 cancels out, moles of H2 cancels out, and we perform the calculation to find that 61.3 grams of H2 had to have reacted to form 345 grams of NH3. When we perform a stoichiometric problem in order to predict the amount of product that we can obtain from a given amount of reactants, what we are calculating there is called the theoretical yield. The theoretical yield is the maximum amount that can be expected to be obtained based on how much we start with. This calculated theoretical yield can often be quite different from the actual yield that we receive when we perform the experiment and run the reaction. The actual yield is how much we actually end up getting. That can be affected by a number of different factors in the reaction, such as how well the reactants actually mix together, and maybe some of the realities of the limitations of the purification processes that we have in order to purify our product. And so it can be useful for us to express how much we actually get as a percent yield. The percent yield gives us a reflection of how much we get compared to how much we could have gotten. It's a pretty easy calculation. All we do is we divide the actual yield, how much material we actually got at the end of the reaction, divided by the theoretical yield, which we calculate through a stoichiometric ratio, and then we multiply that by 100 to convert it to a percent. And so again, the amount of product that we expect to get is based upon our initial stoichiometric calculation. That is our theoretical yield. That is the most amount of product that could be produced based on our amount of reactants. The actual yield is very often less than how much was actually predicted, based on a number of factors, such as impure reactants, maybe there were some byproducts produced, or we had an incomplete reaction. Whatever the case may be, the actual yield is usually less, sometimes a lot less, than the theoretical yield. And we simply calculate it by dividing our actual by our theoretical and multiplying by 100. Let's look at an example that ties all of this back. Earlier, we performed a calculation that told us we could theoretically obtain 4.70 grams of IF3 if we begin with 3.24 grams of I2. So we go into the lab and we run this reaction, and we actually end up obtaining 2.84 grams of IF3. And so in order to calculate our percent yield, we're going to take our actual amount of 2.84 grams, divide that by our theoretical amount that we calculated. We're going to multiply by 100 in order to convert that to a percent, for a percent yield of 60.4%. And so in this video, we've explored the idea of stoichiometric calculations and how we can start to compare the amounts of things in chemical reactions. I hope this has been helpful. If you're looking for some more help, there's lots of different resources on the website to explore.